Okay, so we discussed earlier that covalent bonding is a sharing of electrons, right? So it's a sharing of electrons, and when we looked at covalent bonding, we looked at two models. There was the molecular orbital theory and the valence bond theory. Now, for the most part, we can look at covalent bonding through the valence bond theory, and the valence bond theory states that a sharing of electrons occurs due to orbital overlaps. So they occur through the overlap of orbitals. And you guys are probably aware that there are different types of bonding electrons that can be shared, right? A single bond is when you have a sharing of one pair of electrons, sharing of one pair of bonding electrons. Okay, so I'm just going to kind of abbreviate bonding electrons as BE, right? A double bond is a sharing of two pairs of bonding electrons, right? Double bond sharing of two bonding electron pairs, and a triple bond is a sharing of three bonding electron pairs. Okay, so you guys probably know this from previous courses regarding covalent bonding. Now, when we're looking at these bonds, we also want to look at the length of each bond, right? So each bond has a certain characteristic strength as well as bond length. So what we're going to do is we're going to look at the relationship between bond length and bond strength. So bond length, we can define this as the distance between adjacent nuclei in a covalent bond. And you can also use bond length in terms of ionic bonds, metallic bonds. For the time being, we're going to be looking at covalent bonds. I'm going to abbreviate bond length as BL. We're also going to have something called bond strength, which is the energy required to break or create a covalent bond. Okay, let's abbreviate bond strength as BS. And basically, as the bond length increases, bond strength tends to decrease. Okay, so let's take a look at the single bond, a double bond, and triple bond. So what a single bond will look like, and I'm just going to represent each dot here as a set of nuclei. This is going to be a single bond. A double bond between the nuclei will look kind of like this. Okay, and these are going to be the electrons that I'm kind of demonstrating. So this is the double bond. And a triple bond between the bonding electron pairs is going to kind of look like this. And you can see here that so the triple bond is going to have the shortest bond length, right? And it's going to require the most amount of energy to kind of break apart, right? So we can see that the triple bond has the highest bond length, but the lowest, the highest bond strength. I made a mistake over there. Highest bond strength, but the lowest bond length, right? And the single bond has the highest bond length, but the lowest bond strength. Okay, so this is something that you want to kind of keep in mind, right? So when we're looking at covalent bonds, we're looking at a sharing of electrons, and different numbers of electrons being shared can constitute different types of covalent bonds, whether it being a single bond, a double bond, or a triple bond. Now, when we're looking at covalent bonds in terms of orbitals, we described a covalent bond as an overlap of orbitals. Well, there's two types of orbitals. There are two types of orbital overlaps that can occur. So there's two types of orbital overlaps. So the orbital overlaps that we're going to be looking at can occur directly, so that we have a direct orbital overlap. So a direct orbital overlap is basically where the orbitals will overlap near the nuclei. Okay, And these direct orbital overlaps are called sigma bonds. Okay, so how would we show this if I represented an orbital with a circle? Right, this is one orbital, and I have another orbital. Let's do that in red. Okay, so these are two different orbitals, and let's say that they are s orbitals. Okay, so this is one of the s orbitals, this is the second s orbital. This overlap region is called the sigma bond. Okay, so the sigma bond is basically a direct orbital to orbital overlap. Okay, now this is a sigma bond between two s orbitals, right? You can call this, right, s orbital 1, this is s orbital 2. Right, so sometimes you might commonly see this as an s to s orbital sigma bond. Okay, so that's essentially one type, but you can also have a combination of different orbitals. For instance, if I had one orbital, let's do it in red, and let's say this is an s orbital, and the second orbital, let's do it in green here, it's a p orbital. Right, this overlap here would be the sigma bond. Okay, so we stated earlier that a covalent bond exists when you have an overlap of orbitals. Well, there's different types of orbitals that this can occur in, and that one way that this overlap can occur is a direct overlap between the nuclei. And this is a really strong set of covalent bonds because the nuclei are really close, right? Now, another case where the orbitals can overlap is long range overlap. So this is basically an overlap or covalent bond at a distance. This is a lot weaker, and this is called a pi bond. Okay, so sigma, we use the Greek letter sigma for that, and pi, we can use the Greek letter to represent that. Right, and a pi bond is a long range overlap. So what that would look like if you had a p orbital here and another p orbital here, right, this overlap between the p orbitals constitutes a pi bond, right? And pi bonds only occur between p orbitals. Right, so pi bonds are orbital overlaps at a distance between p orbitals. Okay, so only p orbitals will be involved in a pi bond. They're from a distance, and each of these pi bonds are basically 1/2 pi, so the full set is one full pi bond. Okay, so there's two types of orbital overlaps. There's a sigma bond, which is a direct overlap, and a pi bond, which is a long range overlap. Now, how this kind of relates to our types of covalent bonds, we noted that there's three types of covalent bonds that we looked at: a single bond, a double bond, and a triple bond. Well, a single bond is technically just a sigma bond. So it's one sigma bond. So it's a direct orbital overlap that are really close to the nuclei. A double bond is one sigma bond and one pi bond. So the sigma bond would just be the direct overlap. The pi bond is basically the orbital overlap, the p orbital overlap from a distance. Right? Pi bonds are only between p orbitals, so make sure you remember that. A triple bond is basically one sigma bond plus two pi bonds. Okay, so this material here you guys kind of have to memorize, right? It's going to be really important in understanding some of the fundamentals regarding hybridization, right? You also need to kind of bring up this whole notion that each of these bonds have different bond lengths, right? And each of these bonds also have different bond strengths. Now you can imagine that the triple bond has a stronger bond strength because there's more bonds involved, right? So you have one sigma bond, two pi bonds. Sigma bonds tend to require more energy to break apart than pi bonds, right? But if you have the combination of the two versus just one bond, then it will require more energy. Okay, so let's take a look at hybridization and just some of the combinations. So the single bond is a sigma bond, effectively. A double bond is a sigma bond and a pi bond. And a triple bond is one sigma bond and two pi bonds. Right? And once again, a pi bond is an overlap of p orbitals over distance. So this is one p orbital, and this is another p orbital. And let's say that these p orbitals contain an electron, right? Basically, the pi bond is this overlap. And how this overlap actually occurs, they actually kind of fuse, and it actually creates this round-like structure, right? So they fuse, the orbitals kind of fuse from a long distance, and it allows the electrons to actually cycle through both orbitals. Okay, and then this will also kind of fuse, these orbitals will fuse, and essentially the electron can move through this entire network. So that's kind of how it works, right? And the idea here is that this is really weak in comparison to the sigma bond. Now, one of the issues with this is that we know that a single bond is going to have the longest bond length, and a triple bond is going to have the shortest bond length, right? And in order for us to look at bond length, we have to look at it as inversely proportional to bond strength, right? So as we increase bond length, we actually decrease the bond strength. Now, however, when we're looking at overlaps between different orbitals, right, we can have a sigma bond between any, we can have a single bond anytime we have a sigma bond, right? So this is basically an S to S sigma. This would be an S to P sigma. This would be a P to P sigma. But in this scenario, what's going to happen here is that when you combine different sigma bonds, each constituting a single bond together, the bond lengths will be different. You can imagine that the bond length here would be the highest, and then it would be this bond length, and then this bond length, right? And in this case, the longer the bond length, the weaker the bond strength, right? In any kind of compound, the bond length should all be consistent. If you have a single bond, all the bond lengths should be the same. If you have a double bond, all the bond lengths should be the same. If you have a triple bond, all the bond lengths should be the same. So hybridization is basically a way for different orbitals to fuse together and make sure that their energies of the bonds are consistent. So I'm going to show you guys this through an example, but just kind of keep this in mind. Really just keep this in mind. Right, your two key ideas here is what a sigma bond and a pi bond is, as well as the different types of architecture that you could see in a covalent bond. I'm going to show you this through an example, and in order to really understand this, you guys have to kind of understand electron configuration as well as some of the orbital diagrams. So let's take a look at an example. Let's take a look at methane. Let's take a look at CH4. Okay, so if we're looking at methane, CH4, in this case, if you wanted to draw the Lewis dot structure, right, if this is carbon, let's make the central atom orange here. The Lewis dot structure, right, you can imagine there is 4 bonding atoms, and if you're having a normal covalent bond, you can see that hydrogen receives one of carbon's electrons and donates its own. This hydrogen will receive one of carbon's electrons, donates its own, and so forth. And you'll see that here. Right, so now each hydrogen has access to these 2 electrons, creating a stable octet, and the carbon will have access to all of these 8 electrons. Okay, so now you understand that. Now, beyond this, if you wanted to demonstrate the Lewis dot structure as a structural formula, you can basically think about there being 4 single bonds, right? Because there is basically a pair of bonding electrons being shared between a carbon and a hydrogen. Okay, so there's 4 single bonds. And that equates to 4 sigma bonds. Okay, now how do we show a sigma bond using orbitals, right? So when we're looking at bonding, we want to think about everything in terms of orbitals. Covalent bonds, once again, are valence orbital overlaps. Okay, so what is that? How do we show that using an orbital diagram? Well, first of all, what you guys have to remember here is that a sigma bond occur between half-filled orbitals and pi bonds will occur between half-filled pi orbitals. Okay, so these are two components that you kind of have to address. Now, when we're looking at our structure here, and you guys can demonstrate, if you have a much more complex compound, you can figure out the structural formula by using the formula. Total number of bonds is equal to total number of electrons stable octet minus total number of valence electrons divided by 2, right? So you can kind of revisit this topic going back to the lesson on Lewis dot structures. Anyways, if you're looking at the structure, we said that there was 4 sigma bonds. Let's address our central atom here. Okay, our central atom here is carbon. Okay, so I'm going to represent carbon here, and we know that the electron configuration of carbon is 1s2, 2s2, 2p2. Because bonding is only going to require the valence shell, we're only going to be looking at the 2s2, 2p2. Okay, now the valence shell is composed of valence subshells as well as valence orbitals, right? Now there's 2 subshells in question here. We have the s subshell, the 2s subshell, and the 2p subshell. So if I draw out the valence shell here, carbon is going to have the 2s subshell here and the 2p subshell here. Okay, so I'm going to draw out the subshells shown here. Okay, 2s subshell, the orbital itself is going to be spin paired. 2p, you're going to half fill the orbitals according to Hund's rule. You always half fill before spin pairing. This is what the architecture will look like. Now, in order for you to have a sigma bond, you need a half-filled orbital, right? We said that there should be 4 sigma bonds. There's a sigma bond here, a sigma bond here, here, and here. Okay? So there should be 4 hydrogen bonding atoms, right? Now, if you look at a hydrogen bonding atom, let's do the hydrogens out here. Okay, so the hydrogen should just be 1s, right? And this is what it looks like. This is 1s1. There's 4 of them, however. Because there's 4 of them, you would basically need 4 half-filled orbitals. Now you only can see that there's 2 half-filled orbitals. This is a problem. How do I create 4 half-filled orbitals? So what actually happens here is you can imagine that the 2p subshell is higher in energy than the 2s, right? So even if you did create 4 half-filled electrons, there's going to be problematic because they're going to be different energies. First of all, how do I create 4 half-filled orbitals? Well, in this case, what's going to happen is one of these electrons, that spin pair, it actually transitions. It jumps to a higher energy level. And the reason for that is because when you're looking at elements that are bonding together, there's a surplus of energy, they're colliding with each other, and now this electron can actually transition. So this performs an electron transition. It jumps to a higher energy subshell. Okay, so it jumps to a higher energy subshell, and when it jumps to a higher energy subshell, this is what happens. I'm going to show you the higher energy architecture of carbon now. So now it looks like this: 2s, 2p. Now the electrons, there's going to be 1 electron here, but now we're going to have 3 electrons here. Okay, so this is the high energy state. So you can consider this the excited state. Okay, and now you have 4 of these hydrogens. So you have 4 half-filled orbitals. So technically you can have 4 single bonds or 4 sigma bonds. The only problem with this is that the 2p subshell is going to be higher in energy than the 2s subshell. This will cause the bond lengths to not be the same, right? So in order to correct for this, we want to make sure that all of these orbitals are degenerate. Degenerate means that they have the same energy. And this is where you actually have to fuse the orbitals. you fuse the orbitals and you create something called a hybrid orbital. The hybrid orbital will basically have all of the same energies. That will allow the bond lengths to be the same. Okay? So in order for me to do that, you get a fusion of this 2s orbital with the 3 2p orbitals. When you fuse this together, you create something called a hybrid orbital, and the hybrid orbital, because it consisted of one s orbital and 3 p orbitals, it's called a 2sp3 hybrid orbitals. And this whole thing is called a 2sp3 hybrid subshell. Good. Now, the way that this is actually going to occur, basically you have a mixture of the orbitals. So you have this s orbital here, and I'm just going to draw this out, but you have this s orbital fusing with this p orbital. Actually, you know what? We'll try to draw it this way. I think this would probably make it easier. Okay, here's your p orbital. We have an s orbital that's combining with it. And parts where there's an overlap, there's basically going to be an enlargement of that region. Parts where there isn't an overlap, there's going to be a shrinkage of that region. So if you combine these two together, you'll see something that kind of looks like, I'm just going to redraw it here. See, it's something like that. Okay, and we don't have to draw it accurately, right? But it basically takes the characteristic of the two orbitals, and this forms something called an sp3 hybrid orbital because of the fact that there's 3 p orbitals and 1 s orbital. Okay, so there's going to be different types of hybrid orbitals that are created, but you can understand that this actually elevates in energy a little bit, and this actually gets reduced in energy a little bit, right? And we're going to say energy is on the y-axis. So now you have this 2sp3 hybrid subshell, and there's 4 2sp3 hybrid orbitals. Okay, now that you have these 4 sp3 hybrid orbitals, you can now form a sigma bond with the hydrogen to make sure that the bond length is completely stable. And the reason this bond length is really important to be the same is because you can imagine that this is going to be a tetrahedral structure. Right, so this is going to be a tetrahedral structure. However, and this would only be stable if you have all of the bond lengths being the same. So it can sit upright, it can pack appropriately. If one bond length is bigger than the rest and the other bond lengths are smaller, it's not going to be stable, it cannot pack, its structure will be impaired, right? And that's going to be a problem. So that's why hybridization will occur in the sense that we actually create the equal bond lengths in single bonds. We also create equal bond lengths in double bonds, equal bond lengths in triple bonds. So we have these 4 2sp3 hybrid orbitals, they're half filled, and now you can make a sigma bond with each hydrogen. So this is sigma with hydrogen, sigma with hydrogen, sigma with hydrogen, sigma with hydrogen. Okay, that's essentially what's happening here. How do we demonstrate this? Well, the way you're going to show this, and I'm going to kind of demonstrate here. So we have these 2 sp3 hybrid orbitals, these 4 sp3 hybrid orbitals, and what carbon will look like, there's going to be 1 sp3 hybrid orbital here, 1 sp3 hybrid orbital here. It's going to be 4 in total. 1 sp3 hybrid orbital here. And you guys can just label this 1 sp3 hybrid orbital here. And this is the overlap. The sigma overlap is with the hydrogens. This is the valence s orbital for each hydrogen. Right, and this would represent the sigma bond here. So this is the sigma, the S to sp3 sigma bond, right? And you're going to see that there's 4 of them here. And this should have a tetrahedral geometry. So if you actually look at the geometry here, this angle here should be 109.5 degrees, right? This should come out of the plane of the page, right? and this should go into the plane of the page. Okay, so not only do you show the orbital overlap, you also need to kind of demonstrate in the appropriate VSEPR structure. Now this structure here is called a hybridization map. I think most commonly some people refer to this as a flower diagram, but it just basically shows the overlap of the orbital that is in accordance with valence bond theory. Okay, so that's really the idea behind it. All right, let's draw a hybridization map for the following compound. This is ammonia and H3. So I'm just going to start with the Lewis dot structure, right? Nitrogen is going to be your central atom. I'm going to draw this in blue, and basically it's going to donate 3 of its valence electrons to hydrogen, right? So the hydrogen will reciprocate by donating 1 of its valence electrons. So this way that all the hydrogens here have a stable octet, and this nitrogen also has a stable octet. Now if we construct a structural diagram here, just to kind of demonstrate what type of bonds you would expect, you get a structure that looks like this. So you would expect 3 single bonds, so 3 sigma bonds, but there's also 1 lone pair. Okay, so there's 1 lone pair, there's these 3 sigma bonds, right? Which is basically equating with 3 single bonds. And if you wanted to consider a VSEPR structure, the VSEPR structure of this would be trigonopyramidal, right? So you'd have hydrogen here, 1 hydrogen would go out of the plane of the page, the other hydrogen would go into the plane of the page. So if you guys don't understand this, I would review some of the VSEPR videos. Okay, so let's take a look at how this structure, how this bonding occurs, right? And we're basically using this notion of the valence bond theory, where covalent bonds are basically sharing of electrons, specifically sharing of electron pairs due to the overlap of valence orbitals. Okay, so let's take a look at the central atom here. So let's take a look at this nitrogen. Okay, so if we look at the nitrogen, we know that the electron configuration, you know what, I'm just going to put it up here, but if you look at the nitrogen, we know that the electron configuration is 1s2, nitrogen has 7 electrons, we're looking at elemental nitrogen, right? So it has 7 protons and 7 electrons, so we have 1s2, 2s2, and 2p3. Okay, specifically, we're just looking at the valence electrons, which are found in the valence shell, right? So in this case, you have 2s2, 2p3. So this is what nitrogen's valence shell will look like. So this is 2s2, this is 2p3. Okay, so this is the p subshell, right? And the electrons will be as follows. There will be spin paired here, half filled, half filled, half filled. Okay. Now we have 3 hydrogens here. Now each hydrogen will kind of look like this. Okay, hydrogen is just going to be 1s1. So this is the 1s1 orbital, or you can think about it as the subshell. Okay, so let's do that here. Okay, and there's 3 hydrogens, 3 half-filled orbitals. So off the bat, you can imagine that, okay, we have the right amount of half-filled orbitals, so we can constitute a sigma bond, right? So we can have 3 sigma bonds or 3 single bonds. However, this lone pair also constitutes a set of bonding electrons. We know that the full electron geometry, non-bonding electrons. We know that the full electron geometry is based on the total number of electron groups. So the total number of electron groups is associated with bonding electron pairs, or bonding atoms, as well as lone pairs. In order to make sure that this orbital is the same energy as the other 3 orbitals that will be involved in the sigma bond, we need to hybridize this. Okay, so there's a few rules of hybridization that we can kind of follow. Rules of hybridization. Okay, so we're gonna hybridize all lone pair orbitals lone pair orbitals, or basically spin paired non-bonding electron orbitals around the central atom. And you also want to hybridize all half-filled orbitals that are required to create a sigma bond. Okay, so we know that we need 3 half-filled orbitals required to create a sigma bond, and we would essentially expect them to be the same energy because they're from the same subshell. However, because the 2s2 subshell is found in the valence shell, this orbital here, the spin paired orbital, has to be the same energy as these orbitals. So what we're going to do is we're going to hybridize it. So when we hybridize this, in this case there won't be an electron transition. When we hybridize this, so we're going to hybridize these 2 subshells. When we hybridize this, you're fusing one s orbital with 3 p orbitals, right? So when you fuse one s orbital with 3 p orbitals, right, you get 1s plus 3p. This becomes an sp3 hybrid, right? And this whole thing here is the sp3, and this is in the second energy level, the 2 sp3 hybrid subshell. Each orbital in that hybrid subshell is an example of a 2 sp3 hybrid orbital. So this one orbital here, this is an 2 sp3 hybrid orbital. Okay, and once again, the reason we did this is because this orbital here should be the same energy as these 3 orbitals here. Okay, so that means that you've increased some of the energy here and you've decreased some of the energy here, and we basically met at the halfway point. Okay, so now if we look at this, we've basically fused the orbitals. They have the same energy in order to keep the bond lengths the same, as well as the length of the lone pairs. Okay, so at the end of the day, the orbitals in the valence shell should have the same energy. So we get something like that. And after we get something like this, what's going to happen here is we can get the 3 sigma bonds. So you're going to get one of the sigma bonds with the hydrogen. So this is sigma with the hydrogen. So that's one of these. Second sigma with the hydrogen. It's the second one. And the third sigma with the hydrogen. Okay, and this is what the orbital overlap will look like for ammonia. Right now, I'm going to draw this using a hybridization map, using this as a template. And we basically have these 2 sp3 hybrid orbitals. Well, the way we're going to show this, nitrogen, right? And we can note here that if we're creating an sp3 hybrid, right, you have a combination of a p subshell and an s subshell. Sorry, a p orbital and s orbital. So when you fuse those two together, right, you should get, well, it kind of looks like this, right? But you guys can just label it if you don't want to draw it. Just kind of gets wider. You can write sp3 here, right? So in this case, nitrogen is going to have an sp3 orbital here. This is sp3, this is sp3, this is sp3. Right, we're trying to use this, it's going to be in the form of a trigonal pyramidal structure. Right? It's a type of tetrahedral structure. And we're also going to have an sp3 hybrid orbital for the lone pairs. So the lone pairs are going to be found in an sp3 hybrid orbital, because we want to make sure that all the orbitals in the valence shell that are bonding, that are covalently bonding, involved in the covalent bond, they're basically the same energy, right? So now all of these are actually the same energy, right? So it makes the structure more stable. And that's the whole purpose of hybridization, is to make the structure more stable. And then you get a sigma bond with the hydrogen here, sigma bond with the hydrogen here, sigma bond with the hydrogen here. You can notice that the sigma bonds are purely orbital overlaps, right? So we can color this in here. This is the S to sp3 sigma, S to sp3 sigma, and the S to sp3 sigma, right? And you can notice that I've kind of constructed this using a template that mimics, I'm just gonna show this here, but I've used a template that mimics the trigonal pyramidal structure. Okay, so this angle here should be kind of less than 109.5 degrees. It's approximately 107 degrees. And that's the hybridization map for ammonia. So you also have to hybridize, when you have a lone pair, you have to hybridize that orbital in order to make it the same energy as the orbitals that will constitute the sigma bond. So make sure you guys remember that, right, to make sure to hybridize your lone pairs as well, right? So you guys can actually see here that we looked at a tetrahedral structure, right? This electron geometry here is a tetrahedral structure. And the tetrahedral electron geometry will always have an sp3 hybridization. So keep that in mind. We looked at a previous example of a tetrahedral structure, which included methane, and that also included an sp3 hybrid structure. So whenever you see any tetrahedral electron geometry, it'll have sp3 hybridization. So try to remember that, and we'll look at some more examples of this. Okay, so let's draw a hybridization map of water, H2O. So let's start with the Lewis dot structure. So here's oxygen, right? And oxygen needs 2 more bonding electrons. So it's going to donate 1 to each hydrogen, right? Hydrogen is going to be your bonding atom, oxygen is your central atom. And that's essentially the structure that you'd expect, because now each of the hydrogens are happy. They have these they have access to both of these electrons. They have one of oxygen's electrons, one of its own electrons, and now oxygen has access to this entire structure here. Now, there's a few things to note here is that if we look at oxygen, it has these 2 bonding electron pairs, and it has the 2 lone pairs, right? So we have 2 bonding electron pairs. So if we looked at this as bonding atoms or bonding electron pairs and lone pairs, and n the steric number, which is the total number of electron groups, we basically have 4 electron groups, right? So you guys can go back to VSEPR, review the VSEPR structures for this. But if we have 4 electron groups, then we know that this is a tetrahedral geometry. And what we said regarding a tetrahedral geometry in terms of the valence bond theory, describing covalent bonds, is that there's going to be sp3 hybridization that occurs. Okay, so I'm going to show you guys this again. Right, so we're gonna expect to see sp3 hybridization. So I'm going to draw out oxygen being our central atom. I'm going to draw it out here. But before I do that, let's consider its electron configuration. So if we look at oxygen, which has 8 electrons and 8 protons, because we're looking at elemental oxygen, we should have 1s2, 2s2, 2p4. Okay, the valence shell here should just be this portion here, right? 2s2, 2p4. And what that's going to look like, so here's your 2s, 2p. If we fill this out, we should have a spin paired s orbital. Oh, let's use a different color actually. Sorry. Spin paired. Wow. Sorry guys. Spin paired s orbital, and then we employ Hund's rule, and then we have the 4th electron here. Okay, so this gives us 2 half-filled orbitals and 1 spin paired orbital in the p subshell. Okay, we have these 2 hydrogens, and the hydrogens are going to basically be 1s. But the idea here is that there's 2 lone pairs. And there's these 2 orbitals that represent the 2 lone pairs. And these 2 lone pairs, or these 2 non-bonding electron pairs that we showed here, they need to be the same energy as the bonding electron pairs, which will constitute the sigma bond. In order to make them the same energy, we need to decrease the energy of this p subshell here and increase the energy of the s subshell. So we need to hybridize. Right, so hybridization will occur between this 2s subshell and 2p subshell, so we get hybridization. So let's hybridize these orbitals, and because you're combining one s orbital with 3 p orbitals, you get an sp3 hybrid orbital. Now this sp3 hybrid orbital is going to be found in the second energy level. So collectively, all 4 of these sp3 hybrid orbitals are going to form the 2 sp3 hybrid subshell. Now you can see here that all of these orbitals are actually contain the same energy. Right? This is adequate to make a really stable compound. Remember that compounds want to shed or shave away as much energy as possible. The less energy that the compound has, it's going to become more stable, right? So the more stable it is, the less it will react with other substances because of its low kinetic energy, right? So we have hybridization that's created these hybrid orbitals, this new hybrid subshell, right? So this is basically a single sp3, this 2 sp3 hybrid orbital, right? The next thing that's going to happen here is we're going to have 2 sigma bonds, right? So if we looked at the structure of water here, I'm just going to draw it out, right? Water has 2 bonding atoms, 2 lone pairs. Its molecular shape, although the electron geometry is tetrahedral, the molecular shape here is going to be angular bend V-shaped. Right, so we know that this bond angle here, it's going to be less than 109.5. Because of these 2 lone pairs, it's actually closer to 104.5 degrees. Okay, so I need to show a sigma bond here and a sigma bond here. So I'm going to demonstrate that here. This is going to be one of the sigma bonds with the hydrogen. Here's the second sigma bond with the hydrogen, right? And this is basically what the hybridization of the orbital diagram will look like, right? So this is the orbital diagram with hybridization, and what I'm going to do is I'm going to use this to create an hybridization map of water. Now we know that because we have a fusion of an s subshell, an s orbital with p orbitals, each sp3 orbital will look something like this. So this is going to be a p orbital, right? This is going to be an s orbital, right? If you fuse them together, right, if you'll get something that kind of looks like that, right? But you guys can just label this because there's no way to completely draw this accurately. First of all, we're drawing this in 2 dimensions, but these orbitals are actually going to be 3-dimensional, right? So it's going to be kind of like a contorted cylinder, but we'll just write sp3 and sp3 here. Okay, so that's what we're going to be looking at, and that's what I'm going to draw for my structure. So now my oxygen here will look like that, and I'm going to have an sp3 hybrid orbital here, sp3 hybrid orbital here, right? And we're going to also have an sp3 hybrid orbital here, sp3 hybrid orbital here. So it kind of looks like a 4-leaf clover, but our electrons will have 2 electrons located here, 2 electrons located here. Those are our lone pairs, and this sp3 hybrid orbital will then make a sigma bond with the s orbital of hydrogen. So this is hydrogen, and here's another hydrogen. Okay, so these are both s orbitals. This is an s orbital. So this sigma bond here, you guys should color in the overlap to show the sigma bond. This sigma bond here is an s to sp3 sigma bond. This guy here is an s to sp3 sigma bond as well. Okay, and you guys can also see here that these bonds would be in the plane of the page, right? These guys, on the other hand, the orbitals tend to be out of the plane of the page. One can go out of the plane, one goes into the plane to reduce repulsion forces, right? When electron groups, when non-bonding electron pairs get too close to each other, there is repulsion between the electrons. This type of repulsion force is called steric strain. But you don't need to worry about that when you're drawing this in 2 dimensions. And that's basically your hybridization map of water. All right, let's take a look at drawing a hybridization map for ethene. So ethene is C2H4, and a Lewis dot structure of ethene, I'm just going to do the carbons in blue here. The Lewis dot structure of ethene, you're going to have a double bond between the carbons, as shown, and then a single bond between the hydrogens, as shown. Okay, so you're going to have bonding electron pair here, bonding electron pair here, and so forth. So in this case, each carbon acts as a central atom for the structure. And you can notice here that now the hydrogens have access to this network, and they become stable octets, and then the carbons have access to this full network here. Okay, oh, sorry guys. Yeah, that's right, that was right. Whoops. Each carbon has access to this network here. Okay, so now we fulfill a stable octet. I think it's a lot easier when we take a look at this in structural format, right? Where we're gonna see a structure that kind of looks like this. So now when we look at this, you notice here that each carbon, call this carbon 1 and carbon 2, each carbon has 2 sigma bonds, right? 1 sigma to each hydrogen. And then they also have another sigma bond to the carbon. So this double bond here, which we need to kind of dissect, right? This double bond here is going to consist of a sigma bond. I think what we're going to do here is I'm going to show the sigma bonds in yellow. So there is 3 sigma bonds here. And we're also going to get a pi bond, I'll do that in orange, between the carbon. Okay? So we have 3 sigma and 1 pi. So that's what we need to count for each carbon. You're going to see the same thing that gets mirrored on the other carbon. Okay, so let's take a look at the carbons, and we can imagine that carbon 1 or carbon 2 will have the same network. So let's take a look at carbon 1. Before we do that, we need to understand that carbon is 1s2, 2s2, 2p2, right? This is the electron configuration, but specifically the valence shell is 2s2, 2p2, right? So carbon 1 is going to look like, and just like looking at its valence shell, just the orbital diagram, this is a 2p subshell, and there's 2p2 here. The electrons, this would be spin paired, half filled, and half filled, right? And what we need to have 3 sigma bonds, right? Because we can see here that each carbon will have 3 sigma bonds. Right, and remember that the double bond is basically a single bond, or sigma bond is 1 sigma plus 1 pi bond. So I showed the pi bond in orange, right? So we need 3 sigma bonds, so we need to actually hybridize 3 orbitals to form those sigma bonds. Now in order to do that, in order to create a sigma bond, you need a half-filled orbital first of all. So in order to do that, you need an electron transition, right? So I'm going to promote this electron to jump to this this empty shell here, right? So we have an electron transition, and after the electron transition, we're going to get an excited state, which will look like this, right? This electron basically enters an excited state, right? And now the electrons will kind of look like that, and you can notice here that we've met the 3 half-filled orbital criteria. But the other problem, or the other issue with this, is that you also need a pi bond. There's going to be the existence of a pi bond. Now what is a pi bond? Well, a pi bond is basically it's basically a bond from for a distance bond that involves an unhybridized p orbital. Okay, pi bonds are only specifically occur with unhybridized p orbitals. So if you need an unhybridized p orbital, we need to reserve 1 p orbital for the pi bond. However, we need 3 sigma bonds. So because we need 3 sigma bonds and 1 unhybridized p orbital, we're going to hybridize these first 3. Okay, and you would always hybridize from low energy to high energy, right? And the reason you always hybridize from low energy to high energy is because when you mix the low energy orbitals with the high energy orbitals, the high energy orbitals decrease in energy, low energy orbitals will slightly increase in energy, but overall the system will get more stable, right? So in this case, we're going to combine a 1 2s orbital with 2 2p orbitals. Okay, so here are the 2p orbitals. Okay, we're going to combine it with two of these, right? So we basically have 1s plus 2p orbitals, and we get something called an sp2 hybridization. Okay, so this time we get sp2 hybridization, which we've shown here, right? And now you're going to get this new orbital here, and this is called, well, this new subshell, and this is called the 2sp2 hybrid subshell. This is the 2sp2 hybrid subshell. I'm just going to rewrite that a little bit. And in the sp2 hybrid subshell, there's actually 3 sp2 hybrid orbitals, right? You can see that there, right? These guys are going to be half-filled. However, we didn't hybridize this last orbital here. Okay, this guy is actually by itself. This is unhybridized. So this is an unhybridized. Just sorry about that. Unhybridized p orbital. So this is an unhybridized p orbital, which I'm going to redraw out here. And you can see that it's higher in energy than the rest, right? The reason we didn't hybridize this is because you need an unhybridized p orbital to undergo a pi bond, right? So this is what carbon 1 will look like. Now you can imagine that carbon 2 will have the same bonding architecture, right? So I'm going to redraw carbon 2 for you guys. And carbon 2, you would expect the same idea, right? You would have the 3 sigma bonds because you would just basically mirror it, right? And you can show that here. It would be the same architecture, right? So you would have the 3 sp2, the 2 sp2 hybrid subshells, as shown, and you would also have the 1 unhybridized p orbital, as shown, right? So you'd have half-full orbitals, and also another half-full orbital. Now you need to look at the sigma bonds, right? You need to make sure all the sigma bonds are the same length. Well, one of the sigma bonds, well, 2 of the sigma bonds are with the hydrogen. So this is going to be a sigma with a hydrogen. Sigma with hydrogen, right? Sigma with hydrogen. This is for carbon 1, so that's this carbon here. Carbon 2 is going to get the same thing, right? Because it's going to be bound to 2 other hydrogens. Sigma with hydrogen and sigma with hydrogen. Okay? And then what you're going to see here is carbon 1 is going to have a sigma bond with carbon 2. Carbon with sigma bond with carbon 2. Carbon 2 is going to have a sigma bond with carbon 1. Right? And now you have these unhybridized p orbitals. These guys form the pi bond. So you're going to get a pi bond being created between these unhybridized p orbitals. Okay? That's what it will look like using the orbital diagram, but let's take a look at drawing the hybridization map of this. Okay, we're basically fusing an s orbital. So we're confusing an s orbital with a p orbital. Right, and you should get an sp2 hybrid orbital, right? So I'm going to redraw this using the orbital diagram, right? So we have a carbon here, and we're going to have an sp2 hybrid orbital here. So you're just going to have to label it as sp2. Okay, so you don't have to draw it out specifically, but right, you can draw these flattened disks. So we're going to have another sp2 here, right? between this is, let's call this guy carbon 1. This is carbon 1. Okay, and I'll just show carbon 1 and carbon 2 with different colors. This is carbon 2. This will also have an sp2 hybrid orbital. Okay, let's just use a different color for that. So there's an sp2 here, right? But it'll have the same bonding architecture. sp2 here. And all of these sp2 will actually have the same energy. So this is sp2 and this is sp2, right? First of all, you guys can note here that there is a sigma bond being done here. Okay, so I'm going to show you guys that sigma bond, and this is the sigma bond between the two carbons. Okay, so this sigma bond here is an sp2 to sp2 sigma bond. It's a sigma bond, it's an overlap between two sp2 hybrid orbitals. Okay, you're also going to have a sigma bond between the hydrogens. There's a hydrogen here, there's a hydrogen here. Okay, so you have a sigma bond here. You also have a sigma bond here. Okay, so this sigma bond here is an S to sp2 sigma bond. This is also an S to sp2 sigma bond. Okay, and you would see the same thing here as well. Okay, hydrogen, hydrogen. Okay, so you'll still see the S to sp2 sigma, right? So you can kind of relate that there. Okay, they mean the same thing. Now, the other thing is this unhybridized p orbital. So I'm just going to draw that in purple here. But you have this p orbital. Okay, so there's this p orbital here, and in each p orbital, you're going to expect one electron because it's unhybridized, right? So there's an electron here, there's an electron here. And between these unhybridized p orbitals, what's going to happen here is there's going to be a force of attraction, right? So just use that. Let's use a different color here, but maybe we'll use like blue or something, light blue. And there's basically, this is basically the pi bond. So this is 1/2 pi, and this is another 1/2 pi. Okay, and that's basically what this portion is. This is the pi bond. Okay, so this is the pi bond, right? Here you can see the sigma bonds, right? There's a sigma bond here, right? There's a sigma, these are all sigma bonds. So these are sigma bonds, and there's also sigma bonds here as well. Okay, so that's the idea behind that, and this is basically how you can kind of represent this using a hybridization map. So and you guys can also kind of think about the structure in terms of VSEPR, that this would be trigonal planar, right? So this should be 120 degrees, right? And this also is 120 degrees. And as a common idea to kind of understand is that if you have an electron geometry, if trigonal planar is your electron geometry, this is associated with sp2 hybridization. So whenever you see trigonal planar electron geometry, you should see sp2 hybridization. So keep that in mind, because there will be a presence of a double bond, and when you have a double bond, you need to make sure that you create a set of pi bonds, right? A pi bond which involves an unhybridized p orbital. So keep that in mind. Okay, so let's take a look at the hybridization of ethine. Okay, so ethine, if you look at its structure, it actually looks like this. It's a triple bond. It's a type of molecule called an alkyne. Anyways, we'll take a look at that later. But if we take a look at this molecule here, we can see that carbon is associated with the triple bond, right? And this is the structure here. It's going to be completely linear. And I want to understand the hybridization here. Now we can understand that there's two central atoms. Right? There's a central atom here, so we'll call this central atom 1, and there's another central atom here, central atom 2. Okay, and each carbon is tetravalent. That means it has 4 bonds, right? And what we want to do is I'm going to look at the electron configuration of the central atom. Now you can imagine that the electron configuration of the central atoms would be the same. So this is going to be 1s2, 2s2, 2p2, because carbon has 6 electrons, right? And I'm going to look at specifically its valence shell, right? So the valence shell here is going to look like 2s2 and then 2p2, just like that. Okay, and hydrogen is going to look like 1s1. Okay, now you can notice here that the carbon has, because there's a triple bond, we said that triple bonds, okay, so triple bonds consist of one sigma bond and two pi bonds. Okay, so there's one sigma bond and two pi bonds. We know that to create a sigma bond, you need a half-filled orbital, right, for the central atom, right? Oh, well, luckily for us, we actually have two half-filled orbitals, but for two pi bonds, you need two unhybridized p orbitals. So you need two unhybridized p orbitals, right? So we need one sigma bond, which is you need a half-filled orbital. Right, and we need two unhybridized p orbitals. Well, in this case, we do have two unhybridized p orbitals, but we don't have a half-filled orbital. So what's going to happen here is we're going to have an electron transition, right? The electron transitions to the high energy level when it reacts, right? And when the electron transitions, look what happens. Okay, so now this is the central atom after the electron transition. Okay, so now you can see that there's these four half-filled orbitals, right? But the issue here is we also have another sigma bond with the hydrogen here, right? So there's a sigma with the hydrogen, right? So technically we need two sigma bonds, right? The triple bond itself has one sigma bond, but we need two sigma bonds, one sigma with the carbon to carbon, the other sigma with the carbon to hydrogen, right? Yep. So we need two sigma bonds and we need two pi bonds. Okay, and as a result, we need to have two half-filled orbitals to form the sigma bonds. Now, in order to form a sigma bonds that are basically the same length, right, we need to hybridize this, right? So for hybridizing it, I'm going to hybridize these two to create the two sigma bonds. Okay, so when I hybridize this, this elevates in energy, this reduces in energy, and this is the new hybridized orbitals. Okay, so we have one s orbital plus one p orbital. This forms an sp hybrid orbital. Good. So you can just draw it like that, right? It's going to be a fusion of the two. Okay, so we'll just draw like that because an s orbital will kind of look like, so let's say this is the p orbital. You know what, let's use a different color. Say this is the p orbital, right? This is the s orbital, right? It's going to fuse the two and it's going to form that, right? So basically it creates that. Anyways, when you hybridize these two orbitals, now these guys are relatively the same energy, but we still have these two unhybridized orbitals. Okay, so we still have these guys, which are still higher in energy, and this is basically part of the p orbitals, right? This is the p sub. These are p orbitals. These are part of the p subshell. Okay, so you can think about this as 2px, 2py, 2pz, and then this is still the 2py, 2pz orbital. Okay, but this here is basically, I'm just gonna write this out, but this here basically is the sp hybrid orbitals. Okay, so this is basically the sp subshell. Yeah, so it's the sp hybrid subshell. Good. So that's the sp hybrid subshell, and now you're gonna have to have two sigma bonds, right? So you're gonna have one sigma with hydrogen. So if you're sigmaing with hydrogen, you can see that hydrogen is in blue here. You're gonna have one sigma with hydrogen. This is the sigma with hydrogen. Okay, but then you're also gonna have a sigma bond with the carbon, right? Because one of these, so there's gonna be a sigma here. I'm just gonna highlight the sigma in purple, but there's a sigma bond here, and there's a sigma bond, let's say here. and then the other two bonds in the triple bond it's a pi bond, right? So in this case, you're gonna have a sigma with the carbon, right? And you can imagine that carbon 2 has the same layout as carbon 1, exact same thing, it's the same architect, same structure, right? Same location, really. And this is a sigma with carbon. Now you have these two other bonds, right? So let's take a look at carbon 2's layout. So carbon 2, you would expect to have the same thing. You would have this sp hybrid, right? And you would have these two, and one of them is also going to sigma with hydrogen, because you can notice the same structure there, right? So it sigmas with hydrogen. So let's say this is the hydrogen here, right? We also can sigma with the carbon, because this also has a sigma. It has a sigma bond in the triple bond, right? So sigmas with the carbon, but it also has these two unhybridized p orbitals as well. So it's the same exact layout. Okay. And so you've seen that we've accounted for all of the sigma bonds. Now what we have to account for is the unhybridized p orbital. So there is an unhybridized p orbital here, and this forms one of the pi bonds, right? And there's also an unhybridized p orbital here, and this forms a pi bond. Make sense? So that's how we can demonstrate this using electron configuration. But what I want you to also understand, I'm just going to erase this, but what I want you to also understand is the hybridization diagram, or what we call the flower diagram, right? So this is what it's going to look like. So this is carbon. I'm going to draw carbon first. So this is carbon, right? And it has these two sp hybrid orbitals, right? So this is an sp hybrid orbital. SP, actually, you know what, I'll use orange, probably easier to keep track. So there's an sp hybrid orbital here, there's an sp hybrid orbital here, right? And it basically creates a sigma bond with a hydrogen. Okay, so this is a hydrogen. The hydrogen is just an s orbital, right? So hydrogen is basically an s orbital, right? And then that's the sigma bond here. Okay, so this is the sp sigma bond. Good. The s orbital on the hydrogen, the sp orbital on the carbon, and then they form a sigma bond. And then what you're going to see here is you're going to have an sp to sp sigma with the other carbon. Whoops, let's use this yellow. Okay, so this is the other sp. And this other carbon does the exact same thing, right? And this guy will form a sigma bond with this hydrogen here, which is also an s orbital. Okay, so it forms a sigma bond with this hydrogen here. So once again, this is an sp sigma bond. This region here is an sp sigma bond. Okay. But we also need to account for the pi bonds, right? Now there's going to be two pi bonds. One of the pi bonds is the unhybridized p orbital that's located here. Right? We can notice that each of these unhybridized p orbitals, they contain one electron. So this guy contains one electron. This guy contains one electron, and this forms a pi bond. Okay. And this is like 1/2 pi, and then this is 1/2 pi. See that? So that's one of the pi bonds. The other pi bond is going to be here. Sorry, it's getting a little messy, but it's okay. There's an electron here. There is an electron here, right? And this guy forms a bond this way. I'm going to do a different color. You kind of see that?
Yeah.
Okay. So there's these two pi orbitals. One of them forms, so this is 1/2 pi, and then this here is, you kind of see it here, this is 1/2 pi, right? So technically it actually rolls over. So if you guys look at three-dimensional diagrams, basically it's going to look three-dimensional in the sense that it kind of looks like it looks like an elongated sphere. Okay, but you guys can kind of look that up. Anyways, so that's the hybridization diagram, and this is the electron configuration to demonstrate the hybridization diagram. And this is also using the orbital diagram, right? So that's the idea in describing ethene or ethine. Sorry. So let's create a hybridization map for phosphorus pentafluoride. So before we do that, I'm going to just draw out phosphorus pentafluoride as a Lewis dot structure. I'm going to use my phosphorus here would be my central atom, right? Phosphorus has 5 valence, and you can see that this Lewis dot structure is actually going to violate the octet rule, right? Because now if I donate 1 electron from phosphorus to the fluorines, you can see that it receives 1 back. So now because the phosphorus is surrounded by 5 fluorine atoms, right, it can share has access to a total of 10 electrons, right? So this is what the Lewis dot structure will look like. Obviously this is a violation of the octet rule. However, we're not really too concerned about that. And because if we look at our central atom, I'm just going to use a different color here, but if we look at our central atom, if we looked at number of lone pairs to bonding atoms or bonding electron pairs to the electron groups, which is represented by the steric number, we can notice here that we have 5 bonding atoms, 0 lone pairs to the central atom, and we have 5 electron groups, which constitutes 10 electrons surrounding the central atom. Okay, so this actually implies an electron geometry of trigonal bipyramidal. Okay, so this is really useful, and if we did design this in terms of our VSEPR structure, right, we would basically have 3 in the same plane, 3 fluorines in the same plane, one going out of the plane and one going into the plane, okay, as shown. Yeah, so some of the bond angles associated with this, you can have a 90 degree and a 120 degree bond angle, right? I'm just kind of showing it here, right? And that's the idea, right? So this is basically what the structure will look like. Now I'm going to demonstrate this using an orbital diagram, how these covalent bonds will actually exist, right? So let's take a look at phosphorus. If we look at phosphorus, phosphorus has, if we're looking at elemental phosphorus, phosphorus has an atomic number of 15, which basically implies that the elemental phosphorus will also have 15 electrons. The electron configuration as a result would be 1s2, 2s2, 2p6, and you guys can use your periodic table to actually help you write out your electron configuration, right? Specifically, you just need the valence shell, so you could use a condensed structure. I'm just going to write the full electron configuration out, right? So this is 3s2, right? So that basically would constitute 12 electrons and 3p3. So the valence shell effectively would be this, right? So I'm going to demonstrate what the valence shell will look like, right? You can represent all of this using neon. So this is the condensed formula, right? But just looking at the valence shell here, we're going to have, and we're in the 3rd energy level, so n is equal to 3, right? This is the 3s 2 subshell, right? And this guy is going to have 2 electrons, okay? It's going to be spin paired, and then we'll have the 3p, and this time we have to fill this up using Hund's rule, right? And using Hund's rule, we always half fill orbitals before we spin pair. So I'm going to half fill these orbitals, and that's essentially what the valence shell will look like for phosphorus, right? Now we can understand here that we need 5 bonding atoms, right? So if you look at the structural, all of these should be single bonds, and we know that a single bond is therefore a sigma bond. In order to create a sigma bond, we need half-filled orbitals, right? So we would need 5 half-filled orbitals. On top of that, we need 5 half-filled orbitals that are hybridized, right? And we need to hybridize them to make sure that they are all the same length because they would have the same energy. So we need to hybridize 5 half-filled orbitals. Now, the way we're going to do that, first we need 5 half-filled orbitals. Because we're in the 3rd energy level, you can also imagine that according to Bohr's idea, there should be this infinite number of shells, subshells, and orbitals for every atom. So we should also expect to see that in the 3rd energy level, we should also see the 3d subshell. Now these are going to be completely empty, right? We should see 5 d orbitals as a result. However, because we have a scenario where we need 5 half-filled orbitals, what's going to happen here is this one of these electrons that are spin paired, which are unstable, are actually going to transition. So the electron actually transitions upwards, right? And it jumps to the d subshell. Now the way this will do that, you know, during any kind of chemical reaction, there's going to be an excess amount of energy. However, electrons prefer to be half-filled, right? The thing about spin pairing, it already makes it pretty unstable, right? Electrons will mitigate that instability, those repulsion forces by spin pairing themselves. They'll be spinning in opposite directions, and that will somewhat reduce the repulsion forces. However, in this case, because we have excess amount of energy and we have these empty orbitals, this electron will transition. So here we have an electron transition. The electron jumps to a higher energy level, and this is going to basically be our excited state. So now, I'm going to show the excited state in red. Now we're going to have something like this. So this is 3s2, right? This is the 3p3, right? So you can notice that the only thing that's changed here is that now there's an electron up in the 3d subshell, right? We're still in the third energy level, so now we're going to have half-filled orbital here, half-filled orbital here, here, and here, and now here as well. Okay, I just showed a color to just show that I showed a different color to demonstrate that there has been a change from this ground state to now the newly excited state. Okay, so now that we have this excited state, we need to hybridize these orbitals, right? And we need to hybridize specifically this orbital, these 3 orbitals, as well as this last orbital. And we need to make sure that we have 5 half-filled orbitals, because if we do that, then we can have 5 sigma bonds. Okay, so I'm going to do hybridization, and I'm going to combine one s orbital with 3 p orbitals with 1 d orbital, right? And this is going to create a new hybrid subshell, and this is going to be called the sp3d hybrid subshell. And this hybrid subshell will now have the sp3d hybrid orbitals that make up the subshell. Okay, so this is what the new hybrid orbital will look like, right? I'm going to hybridize these 3, and we'll have these 5 orbitals, right? So this is the sp3d hybrid subshell. So this whole thing here is the hybrid subshell, right? And you can notice that they will all be half-filled, right? In order for you to form 5 sigma bonds, you need to hybridize 5 half-filled orbitals to make sure that the bond lengths are the same size, right? So now that we have this, then we can think about we're going to have 5 sigma bonds, right? So we're going to have a sigma bond in each of these orbitals. So we're going to have sigma with fluorine, sigma with fluorine, sigma with fluorine, sigma with fluorine, and sigma with fluorine. Okay? And that's basically going to be our orbital layout, our orbital diagram layout, right? Now, what we need to understand here is, in terms of the fluorine, if we look at its electron configuration, right, each fluorine is going to form 1 sigma bond. Well, if you look at fluorine, and we'll use a different color here. Okay, let's use purple here. So say we're looking at fluorine here. Okay, so if we're going to look at Say we're looking at fluorine, we can understand that the valence shell of this guy, 1s2, 2s2, 2p, and fluorine normally has 9 electrons in its elemental state, right? So for 2p5, right? Just looking at its valence shell here, right? This is the 2s2, right? 2p5, right? So this should be spin paired, half filled, half filled, half filled, spin pair, and spin pair. So this is essentially what we have. So if you look at fluorine, you can actually see that there are 3 non-bonding electron pairs, and we have 1 set of bonding electron pairs. Well, we need to also hybridize these non-bonding electron pairs, right? So we do have this half-filled orbital that we can actually allow for the sigma bond to be created, but these lone pairs also need to have the same energies in order to keep stability. So we actually need to hybridize all 4 of these, okay? Because there's going to be 3 lone pairs, which represents this guy, and this guy. They need to be hybridized. They need to have the same energy. So if we hybridize all of them, now we basically, right, we'll have basically 1 s orbital plus 3 p orbitals, and this forms an sp3 hybridization. Okay, so this is your sp3 hybridization. Right, maybe I'll just bring this down a little bit. Right, so we have an sp3 hybridization. Right, and then this here is your sp3 hybrid subshell. Okay, so I'm just going to redraw them, but now they're all the same energy, right? So now you can actually see here that, you know, we have a lone pair here, we have a lone pair here, we have a lone pair here, this half-filled orbital, and these are examples of sp3 hybrid orbitals, right? So one of these guys here is an sp3 hybrid orbital. Okay, and we can also understand from that is that we would have a sigma bond with a phosphorus, and you're going to see this for every fluorine. So this is just one fluorine, but you're going to imagine that this occurs 5 times, right? So each of these fluorines will have a sigma bond with the phosphorus, right? So this is, you can notice here, this is an sp3 hybrid orbital. These guys here are sp3d hybrid orbitals. Now, what does that imply? So how do we essentially draw this, right? So if we're drawing a hybridization map, and I'm gonna demonstrate that here. If we do a hybridization map, I'm just gonna erase this. Right, we are gonna think about this as trigonal bipyramidal, right? If we do design a hybridization map, what we're gonna do here is we're going to first put down the phosphorus, okay? And we're gonna have these sp3d hybrid subshells, right? So here's the sp3d, and it is difficult to draw these, so we're just going to draw it like that, right? So this is going to be a combination of the sp3 and and the s and the p, right? So this is an sp3d and the d subshell, sorry, right? We're going to have an sp3d subshell here, and there's an sp3d subshell here, right? And then we're going to make a sigma bond. Well, sorry, we also have one here, sp3d, and an sp3d here. Okay, so you can't draw this too accurately. And then we're going to make a sigma bond with the sp3 hybrid orbital here. Okay, so there's going to be an sp3. Actually, we'll use a different color for this. Let's do purple. So this is sp3 hybrid, right? And this should be tetrahedral in its structure. Now, because we basically have 3 lone pairs, 1 bonding electron, this should tend to be linear. Okay, so this is sp3, 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 and this is going to be what your fluorine is going to look like. Right now, fluorine, each of these fluorines should have a lone pair. Okay, and what's going to happen here is this is going to be the sigma bond as a result. So this is the sp3 to sp3d sigma bond. Okay, now you're going to imagine that there's going to be 5 of these, right? And I don't think there's any point in me drawing this out, but I just want you guys to understand this, right? There's going to be 5 of these, right? Maybe you guys can see it from here. But they basically will have the same layout. Okay, so you just have to look at the bonding architecture for one of them, right? Because they're basically all the same. This is an sp3, 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 but I think you guys get the idea behind this, right? We would put the lone pairs here. But once again, you can notice that we get the sp3d to sp3 sigma bond as well, right? So, and you're going to constantly, you're just going to continue to do that here. Okay, so that's what the hybridization map will look like, guys. Right? I'm not going to finish this off, but I want you guys to try to draw that yourselves, right? And really understand the orbital diagram for that. Okay, so it is somewhat of a complex example, but what you're going to see here is that anything that is trigonal bipyramidal, I'm just going to make a note here, but anything that is trigonal bipyramidal, so anything that has 5 electron groups, right? An electron group is an electron, they're pairs of electrons, so they should have 10 electrons. Anything that has 5 electron groups, right, and this is referring to the electron geometry, they should see an sp3d hybridization. So really watch out for that, right? That you should see this sp3 hybridization. Okay, so we'll take a look at some more examples of more hybridization style questions. All right, let's construct a hybridization map for sulfur hexafluoride. So what I'm going to first do here is I'm going to look at sulfur. So I'm going to do sulfur in orange here. And I'm just going to draw out the Lewis dot structure. So you can imagine that this will also be an example where the octet rule is violated, right? This is going to be similar to our previous example of phosphorus pentafluoride, right? But this time we have 6 bonding atoms. And in this case, we have this fluorine here. Okay, so you can imagine that the fluorines will now have stable octets, but the sulfur now has access to 6 electron groups, right? And that would basically mean that it has access to 12 electrons. So that definitely will violate the octet rule, right? And you can imagine that sulfur with other halogens, the electron density would be too great, and there would be a significant amount of repulsion forces, right? Fluorine is pretty small as it is, so as a result, you can actually have this. However, it's not too stable. If we're looking at this in terms of our VSEPR structure, this is actually going to represent something called octahedral, right? So octahedral structures would basically kind of look like this, right? You're going to have 2 bonds out of the plane for fluorine, right? 1 bond into the plane, it's going to be 180 degrees to each other. The other bond into the plane, right? So sorry, there's going to be 2 bonds in the plane, but they're going to be 180 degrees to each other, and we should have another bond going into the plane, right? And then there's these lone pairs. You can see that each fluorine has 3 lone pairs. Okay, so this is what the VSEPR structure will look like. And now what we want to do here is we want to demonstrate this covalent bonding structure using orbital diagrams, and specifically the valence bond theory, right? So once again, the valence bond theory states that covalent bonds are basically valence orbital overlaps, right? So let's take a look at that. Now I'm going to look at sulfur here. And if I write out the electron configuration of sulfur, which is it has 16 electrons in elemental sulfur, right? Whoops. So elemental sulfur has 16 electrons. So the electron configuration is 1s2, 2s2, 2p6, 3s2, and that's going to constitute 12 electrons, and then 3p4. Okay, so that's going to constitute 16 electrons. Now I'm just specifically worrying or concerned about my valence shell here, which is going to constitute the 3s2 3p4 subshell. Okay, so in this case, what that's going to look like, so this is 3s2, this is 3p4, and because we're in the 3rd energy level, you can also imagine that 3d is present. However, this is completely empty, right? So keep that in mind, guys. And there's basically going to be this S subshell here is going to be spin paired, right? Half filled, half filled, half filled, and then spin paired according to Hund's rule, right? So this is going to be the 3p4. And the reason I considered the D subshell is because you can imagine here that we basically will have 6 sigma bonds. So you would expect to have 6 sigma bonds. In order to have 6 sigma bonds, what you would need to do here is you need to hybridize 6 half-filled orbitals. First of all, we need 6 half-filled orbitals. In order to do that, we need to transition 2 of these electrons to the upper, the empty shells, right? Because we know that electrons prefer to be half shells. So we're going to have an electron transition here, and I also have an electron transition here. In actuality, this electron would transition first. This is easier of a jump, and this electron would transition second, right? So now we're going to have this electron transition, right? And now the 3D subshell will try to be filled. So I'm going to show you guys what that'll look like, and this is going to constitute our new excited state. So this is 3s2, right? 3p4, sorry, 3s1, not 3s2, because now one of the electrons jumped, right? 3s1, right? 3p3, and then 3d, and we should see 3d2. Okay, so this is what the new architecture of the orbitals will look like. Okay, and this is due to the electron transition. And remember that sulfur has 6 valence electrons, right? So now that we have this, what we want to do here is, because we want to create 6 sigma bonds, and we want to make sure that they all have the same energy, and as a result they're the same bond length, we're going to hybridize these orbitals and the subshells together. Okay, so we're going to hybridize all of this together. Okay, and when we do this hybridization, we're basically taking one s orbital, we're adding it with 3 p orbitals, and we're adding 2 d orbitals. And this forms an sp3d2. And this is basically an example of sp3d2 hybridization. And this forms sp3d2 hybrid orbitals. And what those hybrid orbitals will look like, it's going to be a combination of the S, the P, and the D. You guys don't need to worry about what the shape is in actuality. You can label it, but this is basically what the new subshell will look like. Okay, so now there's going to be 6 orbitals, and these are all going to be half-filled. Okay, and I think from our previous lesson, we also said that fluorine, which I'll do in purple, right? Fluorine here is going to basically be sp3, right? It's going to undergo sp3 hybridization, right? So you guys can just kind of review the previous example. Okay, so we have sp3 hybridization, right? And the thing about fluorine is going to have 3 valence electrons, right? And you guys can actually see that here. Okay, so these are 3 valence electrons. So fluorine will basically kind of look like this. So each fluorine will have 1 half-filled orbital, right? So this here is going to be the new sp3d2 hybrid subshell. Okay, and each of these hybrid orbitals are now going to have a sigma bond with the fluorine. Okay, and we can also note that the fluorine will now have a sigma bond with the sulfur, and each fluorine will have a sigma bond with the sulfur, and you're going to see this occur 6 times. Okay, so that's the idea behind it, right? And this is what the orbital diagram will look like. Now I'm going to draw the hybridization map, and we're going to draw this in terms of the octahedral structure because we have 6 electron groups, right? So remember that we said that if the bonding electrons, the lone pairs, and the number of electron groups in this case is 6 bonding electrons, 0 lone pairs, 6 electron groups is going to be octahedral, right? As we showed here, right? What it's going to look like now, I'm just going to draw out the sulfur, right? We're going to have sulfur here, and hopefully I have enough space for this. Maybe I could erase that, right? So I'm going to have a sulfur here, right? We're going to also have an orbital here, an orbital here. We're going to have an orbital that sticks out this way, right? So you don't actually have to draw this perfectly. We're going to have an orbital out here, right? You can create a template afterwards. Orbital here and an orbital here, right? These are the sp3d2 hybrid orbitals, right? And you can label those hybrid orbitals here. This is an sp3d2 hybrid orbital, and so forth. And what you want to do now is put your sp3 hybrid orbitals, and you want to create the sigma bond. So I'm just going to do that in purple. So just do that here. So this is a fluorine, and fluorine should be linear because you have 3 lone pairs, 1 bonding set of atoms, right? It's not too common, but it should be linear. So that's what I'm going to show out here. Okay. As long as you guys label it, you don't need to worry too much about it, right? And I'm just going to label that this is an sp3 hybrid orbital, sp3, sp3, and now you're going to have a lone pair here, a lone pair here, a lone pair here, and also an sp3 here. Okay, and basically where they overlap, where the nuclei overlap, this is going to be your sigma bond. Now this is going to be an sp3d2 to sp3 sigma bond. Okay, and you can construct that throughout, right? So you can kind of keep going with that, but I'm going to let you guys do that out because it does take a little bit of time. So you would just kind of go around and you would draw this, right? So here's another example, right? You would write sp3 out, right? And I'm just going to keep going, right? And so forth. So I'm just going to finish up with that. Right, but you guys understand what's happening here, right? You guys can fix that, but that's how you can actually show your 6 sigma bonds, right? So this is essentially why they call it a flower diagram. Excuse me. This is why they call it a flower diagram, because of the fact that it kind of looks like petals in a flower, right? But so that's the idea regarding the hybridization map associated. Okay, so it's very important for you guys to draw the orbital diagram, right? Hybridize the right number of half-filled orbitals to form sigma bonds. Also hybridize lone pairs as well. Okay, so that's really the idea behind it. And whenever you see an octahedral electron geometry, right? Octahedral electron geometries will basically constitute sp3d2 hybridization, and this is the reason why we've seen that. Okay, so that's the idea. Okay, just to summarize our overview of hybridization, if you have 2 electron groups surrounding a central atom, the electron geometry should be linear, and the hybridization will be sp hybridization, so we should see sp hybrid orbitals. And if this is a central atom, I'm just going to use the circle here to represent central atom. If this is our central atom, we should see an sp hybrid orbital here and sp hybrid orbital here. Okay, and in this case it should be a linear architecture. Okay, so it should be linear, so it's 180 degrees. Okay, so that's basically what it will look like. If you have 3 electron groups, the electron geometry would be trigonal planar, and this would involve sp2 hybridization. That means that we will have sp2 hybrid subshells and sp2 hybrid orbitals, and as a result the central atom will look like this: sp2, sp2, sp2. Right, so it's going to form the trigonal planar dynamic, right? and essentially the bond angle here should be 120 degrees. Okay, if we have 4 electron groups surrounding a central atom, we should see tetrahedral electron geometry. So that's going to look like sp3, right? That's going to involve sp3 hybridization. So we get the creation of an sp3 hybrid subshell, and as a result, we will get sp3 hybrid orbitals in that subshell that make up that subshell. And the central atom here will look like this. Right, so we should have tetrahedral geometry, right? So one's going to go into the page, one goes out of the plane of the page, right? And we should see 109.5 degrees. Good. We have 5 electron groups. We should see trigonal bipyramidal electron geometry. And if we see trigonal bipyramidal electron geometry, we should see sp3d hybridization. If we see sp3d hybridization, what we should see is these sp3d orbitals, which will kind of look like that, right? I'm just going to write that here, but these are sp3d hybrid orbitals, right? Sorry, it's kind of, maybe I should redraw that a little bit, but kind of looks like that, right? So 3 in the plane, 2 out of the plane, and just going to show you guys that, right? One goes out of the plane, one goes into the plane. So that's the idea, right? And then finally, if you have 6 electron groups, this is going to be octahedral. So if it's octahedral, we should have sp3d2 hybridization, and we should have a structure that kind of looks like this, right? So this is sp3d2, right? sp3d2. So 2 in the plane, they're going to be 180 degrees, right? 2 out of the plane of the page, and 2 into the plane of the page. Okay, so they're all going to be sp3d2. Okay, so that's the idea, guys, right? And you want to try to draw it with the VSEPR structure. You want to try to draw it with the VSEPR structure, but that's the summary of hybridization.